Hi, welcome to my YouTube channel Human Learning. I am back with part 5 of the series of lectures that I will be conducting on machine learning, and today's lecture is based upon gradient descent algorithm. Before going through this video, I would highly recommend you to go through my previous videos in this series so that you get a better understanding of what is going on in this video. Having said that, let us get started. So in our previous video, we have seen how to calculate the optimum value of the parameter a and b, that is the slope and the intercept of the line y equals ax plus b, by minimizing the cost function using least square method. But the direct matrix formula for least square method works fine when we are dealing with small number of data sets. But in the real world, this is not the case. In real world, we are faced with millions of data, and therefore calculating the inverse of a matrix and other matrix calculations becomes infeasible. In such case, gradient descent algorithm becomes the hero that we don't deserve but what we need. So what is this gradient descent algorithm? It is an iterative optimization algorithm which is used to find the local minima of a differentiable function. Confused? Just relax. We will proceed in a step-by-step manner to understand this big concept of gradient descent algorithm. Now let this be our cost function as we have defined earlier in our previous videos. Here E is the residual given by this, where small y is the predicted output and capital Y is the actual output. Now when we will substitute this E into our cost function, we can rewrite our cost function as half summation small yi minus capital Yi whole square as shown here. Now we have our predicted output small y represented as a linear function of x, and when we will substitute this y into the cost function, we get E equals half summation axi plus b minus yi whole square, where our cost function will become a function of parameter a and b. So in order to understand gradient descent, let us assume for simplicity that we are dealing with only one sample, that is only one dataset, so our n will becomes 1. Therefore, we can remove the summation sign and our cost function will look something like this. Okay, so first let us draw a graph between cost function e and the parameter a, keeping all the other values as constant. This function is a quadratic function in nature, and therefore when we'll plot this function, it will be a parabola due to the square which is present in E, and therefore our graph will look something like this. Now let us consider a point which is the minima of this curve. This is the point where our cost function or the total error is minimum, and all we have to do in gradient descent is to attain that minima point. For that, consider a point which is shown by green color which lies on this curve. Now when we will increase or decrease the value of the parameter a, the green point will move either upward or downward on this curve depending upon the side where this point lies, that is either to the right of the minima or to the left of the minima. Let us draw a tangent at this point. We can see that the slope of this tangent is positive. Similarly, if you would have taken the point to the left side of the minima, then the slope of the tangent would have become negative. And this factor allows us to determine whether we need to increase the parameter a or decrease it in order to achieve our minimum. Now consider a case when it is on the right side of minima as shown here. If we increase the value of the parameter a, then we will go away from our minimum, and if we decrease the value of parameter a, then we will reach towards the minima. So what we find is that when our slope is positive, that is when we are on the right side of the minima, we have to decrease the value of a, and similarly when the slope is negative, that is on the left side of the minima, then we have to increase the value of the parameter a to reach the point near minimum. Therefore, when we update our parameter a to go towards the minima, we write it as a minus delta a, and this negative sign is due to the fact that when our slope or the delta A is positive, A is decreased, and when it is negative, the A is increased. Similarly, we can write the same for the parameter B. We can also rewrite this as A equals A minus alpha del E upon del A and B equals B minus alpha del E upon del B, where our del E upon del A and del E upon del B represents the slope of this tangent, and alpha is the hyperparameter or the parameter which can be tuned in to reach our goal faster. It is also called as learning rate. You can consider this learning rate as a step size which is taken from the current point to reach the next point closer to the minima. Now let us play with this learning rate a little bit so that you get a better understanding of whatever I have explained here. First, let us take a small step size, that is small value of alpha equal to 0.01. So when you will update this parameter using this value of alpha, then in the first iteration of this update, you might reach this point. Now in the second iteration, you might reach here. Eventually, in the suppose sixth iteration, you reach this minima point. So you can see that by taking a small learning rate, you take baby steps towards reaching your goal. Now you can also take the literal meaning of this learning rate as small learning rate means your model is learning slowly and a higher learning rate means your model is learning very fast. Now let us increase this value of alpha to 1. So in the first iteration you can see that our model has taken a larger step to reach the goal than the previous one, and maybe suppose in the third iteration itself it reaches the minima. Now let us consider a value of alpha which we obtain by hit and trial method equals 1.4, such that in the very first iteration our model reaches minima as shown here. So this is the optimum value of the parameter alpha, which will reduce our number of iterations and help us to reach a minima at a faster rate. Then you might be wondering that till now why we had not made this alpha a very large number such that we will quickly reach the minima. If this is what you are thinking, then unfortunately you are incorrect, because by increasing this alpha more than the optimum value, we can overshoot this minima point as shown here, and it will tend to increase and diverge the value of error rather than decreasing it, as you can see here. So I think now you have a better understanding of how gradient descent algorithm works. So without wasting any further time, let us quickly dive into the mathematics that goes behind the gradient descent algorithm. Now we have our parameter update law as this, which was defined earlier. Also we have our cost function, which was the function of the parameter a and b represented as this. So in order to complete the algorithm, we just need to find the values of del E upon del A and del E upon del B. So first, let us quickly calculate the value of del E upon del A. In the very first step, I have just substituted the value of E into del E upon del A. Now we can take this del upon del A inside the summation and finally differentiate the term inside the bracket with respect to A to get the following. Now we can rewrite axi plus b as small yi. Therefore, our del E upon del A will become equal to summation small yi minus capital Yi times xi. And you remember that this small yi minus capital Yi is the residual term. So therefore, our del E upon del A will simply become summation I equal to 0 to n minus 1 ei xi. Similarly, we can obtain the value of del E upon del B. Now, while differentiating it with respect to B, the only difference is that the term capital Xi will not come into the picture, and the rest is same as del E upon del A. So, therefore our del E upon del V will become summation I equal to 0 to n minus 1 ei. Now therefore we can update our parameter by this formula, where del E upon del A and del E upon del B are given as follows. So in order to write a code for gradient descent algorithm, what do you think will be the steps? I have summarized it by writing a pseudocode. Let me explain it here as it will be helpful for us to write a Python code in future video. So, step number 1. First initialize your parameter a and b with 0 or any small number. Why I am doing this? Remember the green dot we had initialized earlier in our graph? Next is step number 2. Let us call del E upon del A as EA and del B upon del B as EB. First initialize this EA and EB as 0. Then run a simple for loop for variable I going from 0 to capital N minus 1. That is, for all the dataset, run a for loop. Now inside this for loop, let us calculate first the values of small yi and ei, that is the predicted output and the residual. Next, update the following value of EA, that is del E upon del A as EA plus EI xi and EB as EB plus EI as shown here. Finally, update the parameters A and B as A equals A minus alpha EA and B equals B minus alpha EB. So in this pseudocode, these blue lines represent the iteration through each sample, and when we have gone through all the dataset once, it is called as one epoch in machine learning terminology. Sometimes it is not possible to achieve a minima in single epoch. Therefore, we will have to update our parameter through multiple epochs. So what we can do is we can run a for loop for j going from 1 to epoch number of times and execute the code. Now, in order to find where to stop this code, we need to incorporate the cost function into this code. Let us call this half summation ei square as ej. So first let us define capital E as an empty list and initialize the value of ej as 0. Next, update this value of capital EJ as EJ plus half EI square for each dataset, and finally add this value of EJ to E. This way we can have a history of values of cost function for all the number of epochs, that is E equals E0, E1, E2 up to E epoch minus 1 as shown here. Now when we plot this value of E with number of epochs, we get a curve something similar to the one which is shown here. This curve shows that our error is decreasing with epochs, and after a certain number of epochs it reaches its minimum value and will remain to that value, which shows convergence of our error to a minimum value, and this is the point where we need to stop this code. Here we have obtained our optimum values of parameter A and B. Finally, let us understand two important ways of performing gradient descent algorithm. As you can see here, first we are calculating the value of del E upon del A and del E upon del B for the entire dataset and then updating the value of the parameter A and B. This type of gradient descent is called batch gradient descent algorithm. And when we update the value of the parameter after each and every dataset, such type of gradient descent algorithm is known as stochastic gradient descent algorithm. Okay, that's it for this video. In the next video, we'll be coding all these things that we have learned throughout the linear regression series for a real life example. So if you like this video, then please give a thumbs up and do share and subscribe so that I'll be inspired to make more such videos on ML. Also, if you have any queries or suggestions, then do let me know in the comment section below. See you in the next video.